We have discussed Sommerfeld theory of electrical conductivity of metals using the Boltzmann Transport Equation and Fermi Dirac Statistics in our previous lecture. Now today we will see Sommerfeld's theory of thermal conductivity of metals. The mathematical technique or tool is same as you have learnt in your previous lecture. Okay. Actually, we have already discussed the thermal conductivity of metals earlier by using the Drude-Lorentz theory. And you know, Drude-Lorentz theory is a classical theory in which electron is treated like a particle obeying the Maxwell-Boltzmann distribution law. Okay, and we have obtained the expression for thermal conductivity of metals, but you have seen actually the result obtained in Drude-Lorentz theory for thermal conductivity of metals is not in good agreement with the experimental result. In other words, you can say that the Drude-Lorentz theory has some drawback because the data obtained from this theory does not fit well with experimental data or experimental observation. So definitely there was a need to explain the thermal conductivity of metals by an appropriate theory, and this was provided by Sommerfeld. You know, actually Sommerfeld accepted the quantum behavior of electron, and electron does not obey Maxwell-Boltzmann distribution law, but it obeys the Fermi Dirac statistics. So using the Fermi Dirac statistics and Boltzmann Transport Equation, Sommerfeld explained the thermal conductivity of metals, and you will be happy to know that the result obtained by Sommerfeld is in good agreement with the experimental observation. So this is a suitable theory for discussing the thermal conductivity of metals. Okay. When you say you have to deal with the problem of thermal conductivity of metals, definitely instead of electric current, there should be heat current flowing through the metallic specimen. And for the flow of heat current, there should be a temperature gradient instead of the voltage gradient, potential gradient. You know, when you apply a potential gradient across a metallic specimen, then electric current flows. But instead of that, if we apply a temperature gradient, it means you have to maintain the two ends of the metallic specimen at two different temperatures. Then heat flows from the higher temperature to the lower temperature. Okay. And the difference in temperature per unit distance is called temperature gradient. And so due to this temperature gradient, actually electronic system get disturbed. So here the perturbing field is the temperature gradient. Okay. And so that electron will be now in a systematic motion. Okay. Or electron will drift inside the metallic specimen. Okay. Since we have not applied any voltage source across the specimen, or you can say that it is insulated from its surrounding, so there will be no there will be no electric current, or in other words you can say that this electric current vanishes when we replace the voltage gradient by temperature gradient. But due to the systematic drift of free electron, a very weak internal electric field is developed. Okay. So current is zero. Current means electric current, but electric field inside the metallic specimen is not zero. Okay. And that's why when you will apply the transport equation, then the transport equation must contain the term containing electric field. Okay, so in this calculation too, in our transport equation, there will be the perturbing term electric force or electric field. Okay, now let us see. When you talk about the thermal conductivity or thermal conduction in a metallic specimen, actually in a metallic specimen, the thermal energy or heat energy flows by two means. There are two factors due to which this thermal energy is transported. And what are those two means? First one is due to the free electrons, and another is the flow of heat energy due to lattice vibration, or you can say lattice waves. But in our present discussion, we will neglect the transport of heat due to the lattice vibration or lattice waves. It means we will only consider that here transport of thermal energy takes place due to the free electrons of the metal. Okay. So you can see I have shown here a metallic specimen in cylindrical form, but it may be in any form. And I have maintained the two ends of this metallic specimen, let us say A and B, at two different temperatures. The end A is maintained at temperature T1 and end B is maintained at temperature T2, and we assume that T1 is greater than T2. Okay. So in this condition, there will be a flow of thermal energy or heat energy from the end A to the end B. And due to this perturbing field, electrons inside the metallic specimen get disturbed, and its random motion is almost ceased, and there will be a systematic flow or systematic drift of the electron inside this metallic specimen, and by virtue of which an electric field is created. This electric field E is not an external field. We have not applied any voltage source to produce this field, but this field is produced due to the systematic flow of electron, and so it is an internal electric field, but it will affect the motion of the electron. So you must take into account, or you must consider the term containing the electric field in your transport equation. Okay, so you can see here there is no magnetic field, so there will be no magnetic force present in our transport equation, but we have to consider the electric force acting on the electron. So in this condition, if you write the Boltzmann transport equation, what will be that? You can see this Boltzmann transport equation you have studied in very detail in our previous lectures, so you can now write that very equation here. The Boltzmann transport equation in this condition will be this. This is minus EE dot del PF plus V dot del RF plus F minus F naught over tau is equal to 0. This is the form of Boltzmann transport equation which will be applicable here. Okay. Here you know this tau is the relaxation time which represents the mean time or the average time between two successive collisions of the electron with lattice. Okay. And F naught, this is the distribution function in absence of the external field, and F is the distribution function in presence of the external field. Okay. Actually, when you write F here, that means Fermi Dirac distribution function. So F naught is the Fermi Dirac distribution function in absence of the external field, and F is the distribution function in presence of external field. Okay. So this is our Boltzmann transport equation. Actually here I have considered that this electric field which is internally produced here due to the systematic motion of electron, that is directed in x direction. Okay, so electron drift will be also on the on the line x axis. Okay, so Now let us simplify the first two terms, that is del E dot del PF and V dot del RF, in this condition when you consider that electric field is along the x-axis. In this condition we will simplify it. So you can see we have assumed that this E is directed in x direction, so it will have only one component, that is x component. Its y and z component will be 0, and so you can write that E is equal to EXI. Okay, and the drift of electron also takes place on x-axis, so this V is equal to Vxi. Okay, and this gradient of F in momentum space, when you consider momentum as a coordinate, then gradient operator is written as del P. So this del PF will be what? According to the definition of gradient, you can write it as del F by del Pxi plus del F by del Pyj plus del F by del Pzk. Okay, and this del R, this is the gradient operator in position space or geometrical space or physical space, you know. And so this del RF, that is gradient of F in physical space, will be equal to del F by del Xi plus del F by del Yj plus del F by del Zk. Okay. Now let us simplify this force term, this perturbing term, minus EE dot del PF. This is the first term in this transport equation, and let us simplify it. You can write this equation like this. This is minus EXI dot this much. Okay, this is instead of this gradient of F in momentum space. And you know, I dot I will be 1, but I dot j will be 0, I dot k will be 0. So only one terms remains remain here, and this is minus E times Ex times del F by del Px. Okay, and similarly you can see this V dot del Rf. V is since Vxi and del Rf is this much. So when you will take the scalar product, you will get Vx times del F by del x. Okay. So now in the light of these two results, we can write the Boltzmann transport equation in this manner. So this Boltzmann transport equation is now minus Ex times del F by del Px plus Vx del F by del x plus F minus F naught over tau is equal to 0. Okay. And equivalently, you may write it like this. This is F minus F naught over tau equal to Ex del F by del Px minus Vx times del F by del x. Okay. Now actually this transport equation is originally in terms of the position coordinate x and momentum coordinate px. But now we will try to express this transport equation in terms of energy of the electron. Okay, and for that we have to do some algebra, which you will see here. See here, I have written this F minus F naught equal to this much. You have to only multiply by tau. Okay, and so F will be equal to F naught plus Ex tau del F by del Px minus Vx tau del F by del x. Okay. Now in our calculation we also assume that the electric field produced due to the systematic drift of electron and the temperature gradient which we have applied is not very strong, but it is weak. So if the perturbing field is weak, you know, there will be a little change in the distribution function f, and f and f naught will be almost same. And that's why you can write this del f by del px almost equal to del F naught by del Px. Okay, and in the similar manner, this del F by del X will be almost equal to del F naught by del X. Okay, what's the reason behind it? Because our perturbing field is weak. Okay, this is a small. It means you have applied a small temperature gradient. Okay, so under this limiting condition, this equation 1 will become what? You have only to replace this F by F naught, and so you can write F is equal to F naught plus Ex tau times del F naught by del Px minus tau Vx times del F naught by del X. Okay, but as I have told you that we will express this transport equation in terms of energy and temperature gradient instead of this partial derivatives with respect to Px and del X. Okay, so now let us see. This F naught is actually a function of a function. You can say that F naught depends on the temperature gradient. So you can write this del F naught by del X in this manner. This can be written as del F naught by del T times del T by del X. Okay. And F naught, this is actually what? This is Fermi Dirac distribution function, because Sommerfeld has applied Fermi Dirac distribution function to deal with this problem, and so we must recognize this distribution function as Fermi Dirac distribution function. Okay, and you know this Fermi Dirac distribution function is given by this expression. This is 1 over 1 plus e to the power e minus ef over kt. Okay, actually here this K is Boltzmann constant. This is Boltzmann constant. So you can also write it KBT. So I am writing it KBT. Okay. But don't write B here. It will take time. So I have written only K, but this is for Boltzmann constant. Okay. Now you can see our aim is to find this del F naught by del T, and you can see that this F naught is a function of T and E both. Okay, so let us take the partial derivative of this F naught with respect to T. Okay, del F naught by del T will be what? Now let us find it. So you can see this del F naught by del T is written as del T 1 plus e to the power e minus ef over kt whole to the power minus half. Okay, and this is just a function of function, and you can differentiate it with respect to t. So this will be minus 1 over 1 plus e to the power e minus ef over kt whole square times e to the power e minus ef over kt times e minus ef over k times minus 1 over t square. I think you are aware of differentiation, so I am not explaining that term, applying the formula here, because you know it. Okay, and so this del F naught by del T is equal to this much. This is e minus ef over kt square times e to the power e minus ef over kt over 1 plus e minus ef over kt whole square. So this is the partial derivative of this distribution function F naught with respect to temperature T. Okay. Again we will have to find its partial derivative with respect to energy E. Okay. So del F naught by del E, this can be written as del E 1 plus e to the power e minus ef over kt whole to the power minus 1. Okay. Here t will be treated as constant. This is partial differentiation. Only you assume that E is varying. So this is minus 1 over 1 plus e to the power e minus ef over kt whole square times e to the power e minus ef over kt times 1 over kt. And so you can write this del f naught by del E equal to this much. This is minus 1 over kt times e to the power e minus ef over kt over 1 plus e to the power e minus ef over kt whole square. Okay. So now see the form of equation 4 and this equation 3. Okay. And you can relate this del f naught by del t with this del f naught by del E. Okay. In fact, this del f naught by del E, del f naught by del E is already present in the expression for del f naught by del t. Because you can see there is minus 1 over kt this much. So except this, the remaining factor in this equation 3 is E minus EF over T with minus sign. So you can relate these two partial derivatives from equation 3 and 4, and that will be del f naught by del t equal to minus del f naught by del E times this much, E minus EF over T. Okay. So in this way we have expressed this partial derivative of f naught with respect to t in terms of energy. Okay. Now, as you can see in your transport equation, there is the partial derivative of this distribution function f with respect to px. Okay. But del f by del c here, this is your final equation. This is your final equation, del f naught by del px. So now our aim is to express this partial derivative in terms of energy or velocity. Okay. So write this del f naught by del px in this manner. This is del f naught by del E times del E by del px. Okay. But you know, E is the energy of our electron. Electron is treated free. So this is simply its kinetic energy. So E is kinetic energy. So we can write E as px square over 2m. Okay. And when you will differentiate it, you will get that this is equal to del f naught by del E times 2px over 2m. Here this 2 and 2 factor will cancel out, and your result is del f naught by del E times px over m. But you know, px is equal to m times vx. This is simply mass multiplied by velocity. Okay. And so this m and m will also cancel out in numerator and denominator. And our result is del f naught by del px equal to vx times del f naught by del E. So in this way we have obtained del f naught by del px in a suitable form. Okay. And also this del f naught by del t in a suitable form. Now we will use these two results in our equation number 2. Okay. Where you can see f minus f naught will be equal to this much. So now let us use these two results in equation 2. And after using that, you will see, you will get f minus f naught equal to this much. This is E times Ex times tau times Vx del f naught by del E plus tau Vx del f naught by del E times E minus Ef over T times del T by del x, partial derivative of T with respect to x. Okay. And this equation can be simplified as this. I have taken here tau times Vx times del F naught by del E as a common factor, and the remaining terms will be Ex plus E minus Ef over T times del T by del X. Okay. So this is the appropriate form of our transport equation to deal with this proper problem of thermal conductivity of metals. Actually, till now we have casted the transport equation in a proper form for dealing with this particular problem. Okay. So equation 7 is nothing. This is simply the transport equation in present situation in appropriate form. Okay. Now, as you know, electron is fermion, so definitely we have to find, we have to apply Fermi Dirac statistics to deal with the problem. Okay. Now, as you know, this F minus F naught, which is deviation of the distribution function due to the perturbing field, this causes thermal conduction and electrical conduction. This is the cause. As F naught is spherically symmetric, so it does not cause any conduction, any type of conduction, either thermal or electrical. But when this F naught changes, that deviation causes the flow of electron, and that flow of electron causes the thermal conduction and electrical conduction. So now let us, we have to calculate thermal conductivity, and for this we have to find what will be the heat current density. And for finding the heat current density, we have to know about how many electrons are flowing per second through unit area. Okay. So for getting the number of electrons flowing per second through unit area, we will apply the idea of Fermi Dirac statistics. And this idea I have discussed in very detail in my video on electrical conductivity. So here I will not discuss it in more detail because that will take time and video will become longer. You have seen in my earlier lecture that the electrons per unit volume, it means you are considering the volume of the specimen in physical space, in geometrical space, equal to 1. When you say 1, it means either 1 meter cube or 1 centimeter cube. And in volume element dpx, dpy, dpz in momentum space. So how many electrons are present in a unit volume of physical space in this volume element in momentum space? Applying the Fermi Dirac statistics, you know, this number is equal to, if dn0, then this is given by 2 over h cube times f naught times dpx, dpy, dpz. Here, actually, this number of electron has been obtained when no perturbing field has been applied. In absence of perturbing field, this is the number of electrons contained in unit volume of the specimen in a volume element dpx, dpy, dpz in momentum space. Why? Because you know F naught is the occupation probability. So the probability of an electron in a particular energy state in absence of external field is F naught. So when you will multiply this number of quantum states, which is 2 over h cube times this much, by this F naught, you get the number of electron, because electron is a fermion and in each quantum state there will be only one electron. So number of quantum states and number of electrons are same. Okay, and I have discussed it in very detail in my previous video. Okay, but when the external perturbing field, here you can say temperature gradient, is applied, this distribution function gets changed and it becomes F. So in that condition, the number of electron per unit volume in this volume element dpx, dpy, dpz in momentum space will be now dn equal to 2 over h cube times f dpx, dpy, dpz. Okay. Now since f is different from f naught, so there will be a deviation of distribution function, and the out and the that difference causes the electric conduction and the thermal conduction. Okay. So I have mentioned it here. You can see that this f minus f naught is responsible for any type of conduction. Now for getting the expression for thermal conductivity, we will have to think about the thermal current density, that is heat flowing per second through unit area. Heat energy flowing per second through unit area, that is called heat current density or thermal current density. And Jx is here the electric current density. Here electric current density is caused by the internal electric field. Okay. And you have seen in my previous video that this Jx is given like this. This is minus 2 over h cube triple integral or volume integral of E times Vx times f minus f naught dpx, dpy, dpz. Okay. Since E is the electronic charge which is a constant, so you can write this Jx as minus 2e over h cube integral of Vx times f minus f naught times dpx, dpy, dpz. And in the similar manner, this thermal current density, this is given like this. This is 2 over h cube triple integral of E times Vx. Mark it. At the place of this Vx, now there will be energy E. Okay. Energy E. And this minus sign here is due to the negative charge of the electron, and but here there is no charge of electron involved, so this result will be positive. Okay. Now we have calculated the value of f minus f naught earlier, and you can see it in this equation 7. We have already calculated this deviation of f, which is f minus f naught, and this is equal to this much. So now let us use this value of f minus f naught in one of our equations, that is for the equation for Jx. So when you will apply it, I am not turning the page because it will take time. You can do the algebra and you can see after substituting the value of f minus f naught from equation 7 in this equation 8, what will be our result? Jx will be equal to minus 2e over h cube and volume integral of tau Vx square del f naught by del E times Ex plus E minus Ef over tau del T by del X dpx, dpy, dpz. Okay. And in the similar manner, when you will substitute the value of f minus f naught in this equation 9, you will get Qx equal to this much. Okay. This is 2 over h cube triple integral of tau times Vx squared times E del f naught by del E times Ex plus E minus Ef over T del T by del X dpx, dpy, dpz. Okay. As you have learnt in the video on electrical conductivity, this triple integral, which is also you can say volume integral, can be transformed into a single integral, and after converting it into a single integral, its evaluation becomes easy. So let us try to transform this volume integral into a line integral, or you can say a single integral. You have seen that actually this Vx square is equal to V square by 3. I have already explained why I write Vx square equal to V square by 3 in my previous video. So you can watch that. And this dpx, dpy, dpz, this is actually the volume between the two spheres, concentric spheres having radii p and p plus dp in momentum space. You have seen. And this is equal to 4 pi p square dp. Okay. So now we will actually substitute these two values in our equation 10 and also in this equation 11, and then there will be only one variable, and that will be in fact energy, and relative to that we can make the integration. Okay, so replace this Vx square by V square by 3 here in the expression for Jx. Okay, and instead of this dpx dpy we replace this. So now our equation number 10, which you can see here, this will become like this. This is Jx equal to minus 2e over h cube integral 0 to infinity tau v square over 3 del f naught by del e times ex plus e minus ef over t del t by del x times 4 pi p square dp. Okay. In fact, in this equation 2, there are three variables. One is v, another is p, and third one is e. Okay. So if you want to integrate it, or you want to get the value of this integral, you must transform all the variables in terms of only any one variable. And our aim here is to cast this equation in terms of E. Okay, and for this you can see how we can do it. You know, E is the energy of electron, which means kinetic energy, because our electron is free, so its total energy is equal to kinetic energy half mv square. And so this v square is 2e over m. So you can replace this v square by 2e over m. Okay. Again, you know that this E, which is kinetic energy, that is equal to p square over 2m, where p is linear momentum. And so p square is equal to 2me, and p is equal to a square root of 2me. Since p square is 2me, so when you will take the differential, you will get 2p dp equal to 2m dE. Okay, and this 2 and 2 will cancel out, and there will be p dp equal to m dE. So now make these substitutions in the equation for Jx. Okay, so after making these substitutions, the expression for Jx will be now this. This is minus 2e over h cube integral 0 to infinity tau 2e over 3m del f naught by del e times ex plus e minus ef over t del t by del x times 4 pi. You can write it as 4 pi p times p dp. But for p I have written a square root of 2me, and for p dp I have written m dE, which we have seen earlier. So after simplification, you can see that this Jx becomes like this. This is minus 16 pi e 2m to the power half over 3h cube integral 0 to infinity e to the power 3 by 2 tau of e. Here actually this relaxation time depends on energy, and so I have mentioned this e in argument only to indicate that tau is energy dependent. So that I have written this e here. And del f naught by del e times ex plus e over t minus ef over t del t by del x dE. Okay, so in this way we have casted that triple integral in single integral, and here integration will be done with respect to the energy E. Okay, in the similar manner, when you will use all those results in the equation for Qx, you will get I have written it directly. You can check it. You can do the algebra. And you can see that this qx is equal to 16 pi over 3h cube times 2m to the power half integral 0 to infinity e to the power 5 by 2 tau of e del f naught by del e times ex plus e over t minus ef over t del t by del x t. Okay. Now actually to evaluate these two integrals, here we are going to introduce a set of integrals in. Okay. And this in is defined like this. In is equal to, we consider it, in equal to 16 pi over 3h cube times 2m to the power half. You can see this factor is present in above two equations. And integral 0 to infinity tau of e to the power n plus half del f naught by del e de. It means we have not considered this term inside the square bracket here. Here actually n is equal to 1, 2, 3 and so on. So in the light of our assumption that this integral in is equal to this much, you can write equation 12 and 13 in terms of it. You can see in equation 12, E contains a power of 3 by 2. And here in our in the expression for in, there is n plus half power on E. So n plus half is equal to 3 by 2. N plus half is equal to 3 by 2. So n in this case is equal to what? This will be equal to 1. This is equal to 1. Okay. So when you will write the expression for I1, then you have to take n equal to 1 everywhere. Okay. But in this equation number 13, E has a power of 5 by 2. So in this condition, you can say that n plus half is equal to 5 by 2. So n will be equal to 2. So this integral will be represented by I2. Okay. So making the use of this set of integrals in equation 12 and 13, you can easily see that equation 12 now becomes like this. Jx is equal to minus I1 times Ex. Here I1 means when you will take n equal to 1, okay, in this set of integral, okay, and minus ei2 over t del t by del x plus ei1 ef over t del t by del x, okay. And after rearranging the terms, Jx is like this. This is minus E over t times I2 minus I1 EF del t by del x. You can see the algebra. And minus E square I1 EX. This is your first term. Actually, the last two term has been combined by taking minus E over t times del t by del x as a common factor. Okay. And similarly, when you will use that integral in the equation number 13, then you will get that Qx is equal to this. This is I2Ex. See here, 16 pi over 3h cube 2m to the power half and e to the power 5 by 2 when e contains power 5 by 2, n is equal to 2. So this will be I2. Okay, I2Ex plus I3 over t del t by del x. Actually, you can see when this e to the power 5 by t2 will be multiplied by this e, then the power on e will be what? That will be 7 by 2. 5 by 2 plus 1, that will be equal to 7 by 2. And when this is 7 by 2, n will be equal to 3. N will be 3. So you can check it that this term will be now I3 over T del T by del X and minus I2 EF over T del T by del X. Okay. Now again, the last two terms you can see that this 1 over T del T by del X is a common factor. So take it as a common factor. And so Qx is written as I3 over T minus I2 EF over T del T by del X and plus this first term I2 EX. Okay. So in this way we have calculated the value of the electric current density Jx and the thermal current density or heat current density Qx. But as I have told you in the beginning of my lecture that this thermal conductivity is calculated when the voltage source is replaced by the temperature gradient. Okay, or the potential gradient is replaced by the temperature gradient. So in this condition there should be no electric current. Okay, so thermal conductivity can be calculated considering the condition that this Jx is equal to 0. So when Jx will be 0, then the thermal conductivity of a metal can be calculated. Okay. And what the definition of this thermal conductivity you have studied in your lower classes, that this is rate of flow of energy through unit area for unit temperature gradient. And so if K is the thermal conductivity of the metal, then this is defined as minus Qx over del T by del X when Jx is equal to 0. When Jx is 0. Here actually this del T by del X is the temperature gradient, and you know in X direction, if heat is flowing in X direction, then del T by del X must be taken negative, because with increase in X temperature decreases. So this minus sign here actually represents that there is a decrease in temperature with increase in X. So in definition we write minus Qx over del T by del X when Jx is equal to 0. So if now our aim is to find this K, and this is the definition or the expression from which we will calculate it. So we must think about this condition. You have to find the value of Qx, okay? But under this condition, that you have to find the value of Qx when Jx is 0. Here, in this equation 15, Qx is defined, but Jx is not 0. So let us take, if Jx is 0, then what will be Qx? And obtaining that value, when you will substitute in this equation 16, you will get the value of K. So let us first impose the condition that when Jx is 0, then what will happen? See this equation 14 and make this Jx 0. When Jx will be 0, you can see from this equation that in this condition, our Ex, I have not done the algebra, you can do it. Taking Jx 0, obtain the value of Ex, and you will see this is minus 1 over E, I2 over I1t minus Ef over T times del T by del X. So this is the value of Ex when Jx is 0. Okay. So if you want to apply this equation 16 to get the value of K, you must write this value of Ex in the expression of Qx. Okay. So what is the value of Qx under the condition Jx barabar 0? Now we can find it taking Ex equal to this much, in this equation 15. So this Ex will be now replaced by this value which we have obtained under the condition Jx equal to 0. So after substituting this, you can see, you can do the algebra that this Qx will be now equal to I3 over T minus I2 Ef over T del T by del X. Okay. The first term remains at each because it does not contain Ex. But in second term, Ex is present, and now we will write this expression for Ex here. Okay. So the second term is ei2 times minus 1 over E times I2 over I1 T minus Ef over T del T by del X. Okay. And you can see that some term will cancel out. You can do the algebra, and after cancellation or after simplification, you will get that this Qx is equal to this much. This is a very simple calculation. You can do it. So Qx will be equal to I3 over T times, I3 over T minus I2 square over I1 T times del T by del X. Okay. And so minus Qx over del T by del X. See here. This will be equal to simply I2 square over I1 T minus I3 over T. Okay. And if you will take the LCM, this will be this much. So you can see, you can compare this equation 16 and this equation 17. As K is defined like this, and the LHS of this equation is same as the RHS of equation 16. So instead of this factor in LHS, we can write simply K, and that's why you can say that this K is equal to, K means capital K. This represents the what? This represents actually the thermal conductivity. This is equal to this much. So in this way, we have obtained the thermal conductivity of the metal in terms of these integrals I1, I2 and I3. Okay. But what is the actual value of these integrals? Actually, the actual value of these integrals are obtained for the electrons near about the Fermi level. Okay. And you can see this integral In, where n is for 1, 2, 3 and so on. This is defined like this. This is minus 16 pi over times root 2m 3h cube times tau f times Ef to the power n plus half plus pi square over 6 kb t square times del square del E square, that is second order partial derivative with respect to E, tau times e to the power n plus half when E is equal to Em. Actually, this result has been directly written here. So for your examination purpose, you must remember it. You have to remember it. Okay. There is no way to get the result. You have to remember it. Okay. So when we will use this value of the integral In, and for this here, since here is 2, so you have to take n equal to 2, n equal to 1, n equal to 3, and then you can obtain the value of K. I have not done the algebra. After making the use of this integral, finally one can get that this thermal conductivity is equal to pi square over 3 times kb square T n tau E over M. Here E is in the subscript, mark it. This is in fact relaxation time at near for the electrons near the Fermi level or close to the Fermi level. Actually, and this kb is here Boltzmann constant, and n represents the number of electrons per unit volume. Okay. Actually, here I have written the Boltzmann constant by introducing this subscript B to differentiate it with this K. This capital K in LHS is the thermal conductivity, and this K in RHS is Boltzmann constant. So to make a differentiation. Although in books you will find that this K, which is Boltzmann constant, is written in a small letter and thermal conductivity in capital letter. But when you write in practice, there is no, you cannot differentiate this. So I have actually used the subscript KB B here. Okay. So in this way, we have obtained this expression for the thermal conductivity of metals. The calculation was something lengthy, but for your examination purpose, you have to do practice, and practice makes a man perfect. So doing practice, watching the video seriously, you can easily learn it, and you can write your answer regarding this question in your examination. Okay, thank you very much.